As 3i Atlas hurtled through the vast emptiness of the solar system, astronomers around the world could hardly believe their eyes. Detected only months earlier by the Atlas survey in Chile, the interstellar object had already defied every expectation. Unlike Oumuamua or Borisov, whose paths were steeply inclined relative to the solar system's plane, Atlas moved along a trajectory almost perfectly aligned with the ecliptic, the invisible disk traced by the planets as they circle the Sun. Its speed was extraordinary, exceeding 200,000 kilometers per hour as it approached the inner solar system, and its mass estimates, roughly 33 billion tons, placed it among the heaviest interstellar visitors ever recorded. As October 29th approached, when Atlas would skim past Mars at a distance of only 1.36 astronomical units from the Sun, a sense of tense anticipation gripped the astronomical community. The object's unusual trajectory was not the only anomaly. Subtle variations in its brightness suggested an irregular shape or perhaps rotation, far faster than any natural body of comparable size should withstand. Instruments tracking the object reported fluctuations every 11.6 seconds, a rhythm that puzzled scientists. Was this the result of an uneven surface catching sunlight, or the signature of an unknown process? The stakes of its Mars flyby were enormous. For decades, interstellar objects had passed the solar system without incident, merely offering glimpses of other star systems' icy remnants. Atlas was different. Its near alignment with the planetary plane meant that its gravitational interactions with Mars and the inner planets would be amplified, potentially altering its path in unpredictable ways. NASA's Deep Space Network and ESA's ground-based telescopes began constant monitoring, calculating every possible orbital permutation. Simulations indicated that even a small deviation at perihelion could redirect Atlas into a trajectory that intersected with Mars' orbit within days, an unprecedented scenario for a hyperbolic object of interstellar origin. Meanwhile, theoretical physicists like Michio Kaku weighed in publicly, reminding audiences that the object's speed and trajectory open the door to interactions not normally considered. If Atlas behaves like a natural comet, we'll see minor outgassing effects, perhaps slight orbital perturbations, Kaku explained during a televised interview. But if there's anything unusual in its structure or energy release, the flyby of Mars could trigger phenomena we've never observed. The physics involved is extreme, bordering on science we've only speculated about. Observatories on Earth and in Mars orbit braced for the encounter. The Mars Reconnaissance Orbiter, usually tasked with mapping the surface, was retargeted to monitor Atlas's approach, its high-resolution cameras snapping frequent images to detect any sudden changes in brightness or trajectory. At the same time, the ExoMars Trace Gas Orbiter scanned for faint emissions that could suggest sublimation or energetic phenomena from the comet's surface. Amateur astronomers worldwide joined the effort, adjusting telescopes to capture fleeting glimpses during windows of visibility, sharing data in real time with professionals. All of them noted the strange consistency in Atlas's luminosity curve, brightening and dimming in precise intervals, a pattern that could not be readily explained by tumbling alone. As Atlas closed in, its trajectory calculations were continuously updated. Planetary scientists ran thousands of simulations, modeling interactions with solar radiation, Mars gravity, and the Sun's intense tidal forces. Even minor errors in mass estimation could lead to vastly different outcomes, including slight deflections that might amplify into larger deviations after the flyby. By October 27th, it became clear that the object would pass within a hair's breadth of Mars, closer than any known interstellar object had come to a planet in recorded history. The potential for observation was unprecedented, but so too was the risk of miscalculation. Scientists debated publicly and privately. Was Atlas a natural object, or could its unusual alignment and rhythmic brightness indicate something more complex, perhaps even artificial? The idea was controversial, but could not be dismissed. A natural comet's arrival is random, scattered across all inclinations. Atlas's near-perfect alignment with the ecliptic was statistically extraordinary, a trajectory that mirrored planetary orbits with uncanny precision. Was it a cosmic coincidence, or was it the mark of design? The Orth effect, a principle known in astronautical engineering, became central to the conversation. If Atlas carried any form of propulsion or engineered mechanism, Its passage near Mars offered an opportunity to leverage planetary gravity to alter its trajectory. Even a modest adjustment at hypervelocity speeds could have massive downstream effects. Observers considered what kind of energy would be required to execute a retrograde burn at perihelion, sufficient to capture Atlas into a bound orbit around the Sun, or to deliberately pass near Mars to calculated distance. Chemical propulsion would be insufficient. Only theoretical nuclear or exotic propulsion could produce the required delta-V without exceeding the mass of the object itself. Yet, the peculiar energy emissions recorded from Atlas in September suggested something beyond sublimation, as if the comet had a mechanism capable of precise, directional energy release. When the flyby finally occurred on October 29, 2025, instruments recorded a surge of reflected light and minor plasma outflows, though nothing catastrophic. Mars's orbit remained unchanged, and preliminary data indicated that Atlas had passed within 3 million kilometers of the planet, dangerously close on an astronomical scale, yet still shy of collision. Scientists exhaled, but the analysis revealed subtler anomalies. The object's rotation rate changed slightly post-flyby, implying a transfer of angular momentum during the encounter. Minor deviations in its hyperbolic trajectory were detected, larger than those predicted by gravitational interaction alone. Some argued this could be explained by outgassing or interaction with solar radiation pressure, yet the periodicity of the fluctuations persisted, still matching the 11.6-second cycle noted from months earlier. These findings reignited debate: natural physics or deliberate control. Data from the Mars orbiters indicated faint, coherent bursts of electromagnetic radiation coinciding with the flyby. The pulses were weak, nearly at the threshold of detection, but structured enough to suggest an organized source rather than random plasma interactions. Michio Kaku weighed in again. We must consider the possibility that Atlas is not merely a passive traveler. Its alignment, its rhythmic pulses, and these faint electromagnetic signals, taken together, hint at an intelligence, or at least a mechanism, operating in ways we cannot yet comprehend. Scientists worked feverishly to model every known scenario. Could a previously unobserved form of cometary behavior explain the anomalies? Could solar wind, combined with Atlas's rotation and composition, produce the observed periodicity and electromagnetic signals? Most simulations failed to replicate all recorded effects simultaneously. As days turned into weeks, Atlas receded into the outer solar system, gradually disappearing from view. But the impact of its flyby continued to ripple through the scientific community. Papers were written, conferences convened, and discussions of interstellar engineering entered mainstream debate for the first time. Some theorists speculated that Atlas might have been a reconnaissance probe from another star system, using its hyperbolic path to gather data or test interactions with planetary systems. Others cautioned against anthropomorphizing, arguing that natural explanations, however improbable, must be exhausted before entertaining artificial hypotheses. Kaku remained measured but persistent in his commentary. We are learning to think on a galactic scale. Objects like Atlas remind us that our solar system is not isolated. The universe is far more active and interconnected than we ever imagined. By December 2025, Thrisma I Atlas had vanished beyond Mars's orbit, leaving only traces of its passage. The rhythmic light fluctuations, the faint electromagnetic pulses, and the data recorded by orbiters and telescopes around the world. These anomalies continued to be analyzed for months, forming the basis of studies in astrophysics, planetary defense, and the emerging field of interstellar object intelligence. While no immediate threat was posed, Atlas had rewritten the rules of observation. Its close flyby of Mars offered humanity a glimpse into the possibilities of interstellar phenomena that could not be fully explained by conventional physics alone. In private communications, NASA engineers and ELA scientists speculated about its structure. Hollow or highly reflective, perhaps an engineered lattice or an unusual configuration of cometary ices. The 11.6-second rotational rhythm, persistent before and after the flyby, remained a mystery. Could it be a natural resonance, a signature of its formation, or a signal intentionally designed to be detected by observers in the solar system? Michio Kaku's final public statements of the year reflected the mixture of excitement and unease that the global scientific community shared. Whether natural or artificial, 3i Atlas challenges us to reconsider the assumptions of interstellar travel, orbital mechanics, and the limits of cosmic engineering. We observed the impossible, and in doing so, we expanded the boundaries of what we can imagine. As Atlas receded into the outer solar system, instruments continued to detect anomalies in its behavior and emissions, subtle but undeniable, forcing scientists to reconsider everything they thought they knew about interstellar objects. The Mars orbiters reported faint coherent electromagnetic pulses, each aligned with the 11.6-second rotational rhythm previously observed. Analysis suggested these pulses were not random noise. They carried harmonic structures, almost mathematical in nature, patterns that could not be easily explained by natural plasma dynamics. Michio Kaku appeared on several broadcasts emphasizing the stakes. If Atlas is merely a comet, this is unprecedented behavior. If it is engineered, then we are witnessing technology operating on a scale that dwarfs anything humanity has attempted. The question is not just what it is, but why it is here and what it is capable of. Amateur astronomers and professional observatories alike scramble to gather every fragment of data. The Vera Rubin Observatory captured faint optical glints in the outer solar system, and radio telescopes detected minute modulations in the emissions that aligned with Fibonacci sequences, a level of mathematical sophistication highly unlikely to occur in a purely natural object. Some researchers suggested that the object might be tuning itself, adapting its emissions for detection by intelligent life in the inner solar system. Others were more cautious, proposing that resonance effects or previously unmodelled interactions with the solar wind could produce similar patterns. By late November 2025, attention shifted to the long-term implications of the flyby. Atlas's trajectory, although hyperbolic, had been subtly altered by Mars's gravity, a small but measurable deflection that aligned more closely with the ecliptic than before. The change was slight but statistically significant. Combined with the rotational and electromagnetic anomalies, it raised the possibility that Atlas's behavior was being actively managed rather than dictated by random forces. Space agencies began to treat Atlas as a priority target for interstellar observation. The James Webb Space Telescope was tasked with capturing high-resolution images of its outer coma and tail when geometry allowed, while the Hubble Space Telescope attempted spectroscopic analysis to determine composition. Preliminary results confirmed a complex mixture of volatile ices, silicates, and a previously unobserved reflective surface structure, suggesting either an unusual natural formation or some form of artificial design. Discussions within NASA and ESA took on a new urgency as Project Helios scientists considered the possible energy requirements for Atlas's persistent electromagnetic pulses. Calculations indicated that the energy emitted exceeded what could be generated by sublimation or rotation alone, implying an internal mechanism or process beyond conventional cometary physics. By December, reports from the Parker Solar Probe detected microbursts of charged particles correlating precisely with the object's rotational period. The bursts were directional, forming coherent beams that appeared to interact with the solar magnetic field. Experts at the Max Planck Institute performed complex magnetohydrodynamic simulations to explain the phenomena, but the results failed to match observations. The pulse's directionality and regularity suggested that Atlas might be harnessing external forces in ways previously thought impossible, a kind of interstellar engineering. As the anomaly persisted, public fascination grew. News outlets ran stories speculating on intelligent life, advanced alien technology, and the implications of a potentially engineered interstellar probe. Headlines such as Comet or Cosmic Sentinel and 3i Atlas, the visitor that defies physics, spread across the globe. Michio Kaku appeared on multiple platforms to provide context, warning against sensationalism while acknowledging the mystery's gravity. We are looking at something that challenges the foundations of astrophysics. Whether it is natural or artificial, we are witnessing a process that the universe rarely allows us to observe firsthand. Meanwhile, internal NASA documents leaked, revealing that the agency had considered the possibility of Atlas performing intentional maneuvers using solar radiation or magnetic fields to alter its trajectory subtly. Though officially dismissed as speculative, these internal discussions signaled the seriousness with which engineers and astrophysicists were approaching the anomaly. By early January 2026, the object had passed beyond Mars orbit yet its emissions continued, faintly detectable in the outer solar system. Observatories reported an increase in harmonic complexity, with the Fibonacci sequences evolving into higher-order mathematical structures. Some researchers suggested this could represent a message, or at least a system of communication, although the lack of a decoding key made definitive conclusions impossible. Michio Kaku, invited to lecture at MIT, warned that assuming intent could be dangerous, but he also highlighted the unprecedented alignment of factors: the ecliptic skimming trajectory, the periodic electromagnetic emissions, the modulation in harmonic frequencies, and the anomalous brightness fluctuations. Together, they presented a scenario unlike any observed before. By February, a global coalition of observatories and space agencies established continuous monitoring protocols, creating a virtual network to track the object's emissions in real time. Satellites from multiple countries synchronized their measurements, attempting to triangulate the source and measure its power output accurately. Analysis revealed that the pulses were interacting with the solar wind in subtle ways, generating ripples that propagated throughout the inner solar system. Some speculated that these ripples could serve as a method of signaling, or even as a form of energy transfer, although the mechanism remained speculative. Public interest remained intense. Science communicators and journalists debated the possibilities, blending fact with speculation, while experts cautioned that without direct evidence, any claims of artificiality remained unconfirmed. Michio Kaku maintained a careful balance, acknowledging the strange phenomena while emphasizing the importance of rigorous scientific methodology. As March approached, scientists noted yet another anomaly. The previously measured rotational period of 11.6 seconds had shifted slightly, now occurring every 11.4 seconds. While small, the deviation was consistent and repeatable. Researchers debated whether this reflected a structural change within Atlas, an interaction with solar or planetary forces, or a deliberate adjustment of some kind. The combination of these factors, trajectory alignment, electromagnetic pulses, harmonic modulation, and rotational shifts, made Atlas arguably the most significant interstellar object ever observed. It had challenged assumptions about the randomness of cometary paths, the limits of natural physics, and the potential for interstellar engineering. Michio Kaku addressed the scientific community directly in April 2026, emphasizing both caution and wonder. Atlas has shown us that the universe can surprise us in ways we cannot predict. We are witnessing the frontiers of physics, astronomy, and potentially interstellar technology all at once. Whether this object is natural or artificial, it has already transformed our understanding of what is possible. By late spring, data analysis revealed a subtle increase in reflected energy from the object as it receded toward Jupiter's orbit. The reflective surface, initially thought to be dust or ice, appeared to maintain its coherence over vast distances. Some theorists speculated that Atlas was designed to survive interstellar transit with structural integrity intact, a hypothesis supported by the observed rotational stability despite passing near the Sun and interacting with planetary gravity. Kaku described it as the most remarkable test of astrophysical resilience ever recorded. Scientists continued to model potential interactions with other planets, speculating on whether future encounters might reveal additional anomalies or signs of energy release. Simulations suggested that Atlas's path through the solar system could create measurable gravitational effects on minor bodies, but nothing catastrophic. Its hyperbolic velocity ensured that it would eventually leave the Sun's influence entirely, disappearing into interstellar space, perhaps to be observed by another civilization in the distant future. Public fascination remained at its peak. Documentaries, podcasts, and news specials explored the flyby, emphasizing both the known facts and the lingering mysteries. Michio Kaku's commentary became the authoritative voice guiding public understanding, balancing the awe-inspiring possibilities with scientific caution. In June 2026, astronomers detected the final faint pulses of radiation before Atlas left the inner solar system's detectable range. The object's rhythmic emissions gradually faded, leaving only subtle traces recorded in planetary magnetospheres and the solar wind. While Atlas itself was no longer directly observable, its passage had fundamentally changed human understanding of interstellar visitors, the potential for extraterrestrial engineering, and the subtle complexities of orbital dynamics. Scientists compiled an unprecedented archive of data, light curves, electromagnetic signals, trajectory deviations, and rotational periods, establishing a baseline for future interstellar object studies. Michio Kaku summarized the event's significance in a public lecture. 3I Atlas was more than a comet. It was a revelation. In observing its passage, we glimpse the edges of what is physically possible in the universe. It reminds us that the cosmos is vast, full of surprises, and perhaps inhabited by intelligence far beyond our understanding. Though the object itself became too distant for direct observation, its influence persisted, etched into the subtle shifts in planetary magnetospheres, faint ripples in the solar wind, and the harmonic residuals recorded by Earth-based radio telescopes. Researchers discovered that the 11.4-second rotational pattern remained detectable, albeit at diminished intensity, suggesting that whatever mechanism drove Atlas's pulses was resilient across millions of kilometers. Michio Kaku described this persistence as an echo of interstellar engineering, a whisper from another star system. Scientists debated the implications. If Atlas was engineered, its creators had designed it to operate autonomously over vast distances and timescales, able to withstand extreme heat near the Sun, gravitational interactions with Mars, and the tenuous forces of outer space. Others argued that the object's behavior could still be explained through complex natural processes, though such explanations strained the limits of known physics. By late 2026, teams at NASA, ESA, and international observatories began synthesizing data into comprehensive models, reconstructing Atlas's trajectory, rotational behavior, and energy emissions. Simulations revealed that its flyby of Mars had altered not only its trajectory, but also the phase and intensity of its electromagnetic pulses, as if the encounter had triggered a response or adjustment. The consistency of these adjustments over subsequent months reinforced the idea that Atlas's emissions were not random, a point emphasized in Kaku's lectures. He reminded audiences that even small energy emissions in the solar wind could propagate vast distances, subtly affecting planetary environments and perhaps even communicating information across astronomical scales. Some theorists proposed that Atlas could be part of a network of interstellar probes, each engineered to interact with stars and planetary systems, leaving behind detectable signatures as a means of mapping or tuning the galaxy. The object's repeated harmonic emissions, Fibonacci sequences, and structural resilience suggested a design optimized for detection and durability. By 2027, the data prompted the development of a new field of astrophysical research, interstellar signal archaeology, a discipline focused on identifying and interpreting structured energy emissions from celestial bodies that might indicate intelligent origin. Academic papers explored whether Atlas's pulses could encode information, while spacecraft engineers debated the feasibility of constructing probes capable of similar feats. Some simulations suggested that even modest propulsion integrated with solar energy collection could allow an interstellar probe to adjust trajectory, rotation, and emissions autonomously, reinforcing the plausibility of the artificial hypothesis. Public interest remained high, fueled by documentaries, news specials, and virtual observatory events that allowed laypeople to follow Atlas's fading signal. Michio Kaku, often the voice bridging the technical and public discourse, cautioned that speculation must remain grounded in observation, but he also encouraged curiosity and imaginative interpretation. Even if Atlas is natural, he said, its behavior has challenged our assumptions, stretched our models, and inspired us to think about what is possible in the cosmos. In mid-2027, researchers reported that Atlas's signal had decreased to near background levels, detectable only by the most sensitive instruments. Still, the object's passage had left a lasting imprint on human science. Theories about interstellar engineering, autonomous probes, and galactic-scale networks became subjects of legitimate scientific inquiry. Michio Kaku summarized the event's significance in a keynote address at the International Astronomical Union. 3I Atlas has shown us that the universe may be alive with activity far beyond our perception. Whether it is a natural object or a creation of an advanced civilization, its passage has rewritten our understanding of the solar system and the potential for intelligent design on a galactic scale. We have glimpsed the extraordinary, and in doing so, we have expanded the horizons of human curiosity. Decades later, students of astrophysics continued to study the archived data from Atlas's flyby of Mars, tracing its trajectory, analyzing harmonic signals, and speculating about the underlying causes. The interstellar object became a case study in anomaly detection, planetary defense, and the possibilities of interstellar engineering. The faint rhythmic pulses that once echoed across the solar wind were described in textbooks as the first recorded evidence of structured energy emissions from an interstellar object, and Michio Kaku's lectures were cited as foundational interpretations bridging science and imagination. The story of 3i Atlas transformed from a tense, uncertain flyby to a profound lesson in observation, modelling, and the boundless potential of cosmic phenomena. Its passage reminded humanity that the universe is not a static void, but a dynamic, interconnected expanse, capable of surprising even the most experienced scientists. Some speculated that Atlas was only the first of many such objects, a harbinger of an interstellar reality we were only beginning to comprehend. The Sun, Mars, and the inner planets continued their courses, unaffected in orbit, but subtly influenced in ways measurable only by careful instruments. The lessons of Atlas endured: meticulous observation, openness to the improbable, and the recognition that in the vast cosmos, events of profound significance can occur quietly, without warning, challenging humanity's place in the universe. Michio Kaku concluded in a reflective essay for Scientific American, "We observed a visitor from beyond the stars, one that defied expectations and challenged the boundaries of physics. Whether it was a comet, a probe, or something we cannot yet define, it reminded us that the universe is alive with possibility. And in looking carefully, listening closely, and thinking boldly, we began to understand that our solar system, our planet, and even our species are part of a much larger story, one in which we are both observers and participants in the cosmic ballet." The legacy of 3i Atlas endured not as a singular event, but as a transformative lens through which scientists, educators, and the public approach the study of space. Its near miss with Mars, the strange rotational periodicity, and the persistent electromagnetic emissions became reference points for the next generation of interstellar research, guiding humanity toward a new era of understanding, exploration, and wonder. In the decades that followed, astronomers tracked hundreds of other interstellar objects, comparing them against Atlas's data, searching for patterns, signals, or repetitions that might indicate a broader network of interstellar phenomena. Each detection was a reminder that the universe is far more complex, structured, and perhaps intelligent than previously believed. 3i Atlas had passed quietly, but its story resonated across time, inspiring curiosity, advancing science, and challenging humanity to look beyond the familiar, to consider the extraordinary possibilities that lie in the dark expanses between the stars.
When you look up at the night sky, you are not just seeing stars. You are looking into deep time. Each point of light is a fossil of creation, shining from billions of years ago. And sometimes, across that ancient ocean of space, something moves. Something not born of our Sunday, a messenger from another system carrying the chemistry of a world we will never see. But before we move on, I want to know where you're watching from. Let me know in the comments. Right now, one such messenger is here. 3i Atlas, the third confirmed interstellar object ever observed, is racing through our solar system, and for the first time in human history, we've caught one of these travelers releasing water. Not speculation, not rumor, real data verified through ultraviolet light by NASA's Neil Gehrels Swift Observatory. A comet from another star system is venting water vapor into our sunlight. That should be impossible. But that's not all. This implicates something that will change everything we knew so far. Hear me out. At its current distance, nearly 3 astronomical units from the Sun, about 450 million kilometers, sunlight is too weak to thaw even carbon dioxide, let alone water ice. A comet born in our own solar system would still be asleep out there, its surface locked in, deep freeze. Yet 3i Atlas is alive, breathing vapor into space, carving a glowing coma, thousands of kilometers wide. So what woke it? The answer may lie in the physics of light, dust, and memory. And it begins with a faint ultraviolet whisper, detected in late July 2025. The signal came from a place beyond Earth's atmosphere, the only vantage where ultraviolet light survives. Swift's ultraviolet, divided by optical telescope, gathered photons that no ground-based mirror could ever see. Over nights of long exposures, scientists stacked the data, canceled the noise, and found what they were hunting for. A narrow emission line near 308 nanometers. The spectral fingerprint of hydroxyl, or OH. Hydroxyl is what's left when sunlight tears a water molecule apart. Wherever we find it, we find water's ghost. From that single spectral line, researchers could reconstruct the outgassing rate. Their models yielded a staggering number, roughly 40 kilograms of water per second, about 88 pounds every second, equivalent to a fire hose pumping nonstop in the vacuum of space. This is the first direct detection of water from an interstellar comet. The first time we've heard another star system breathe through chemistry, we recognize, and yet the deeper scientists look, the stranger it became. Because the physics doesn't add up if we imagine a smooth, solid comet sublimating from its surface. At 3 astronomical units, the sunlight simply isn't strong enough. Something else must be happening. The leading model now is an extended source, a swarm of tiny, ice-coated dust grains ejected from the comet's surface. These grains, no larger than particles of smoke, absorb sunlight far more efficiently than the nucleus does. Their surface-to-volume ratio is immense, and as they drift outward, the weak solar warmth is enough to vaporize their thin, icy shells. In effect, each grain becomes its own miniature comet, releasing water in a vast cloud around the nucleus. That is why the ultraviolet glow is so spread out, why it doesn't fit a point source, and why 3I Atlas seems to have awakened too early. The sunlight may not reach the heart of the comet, but it bathes its dust in enough energy to trigger a slow, steady evaporation. It's a subtle process, and it means this object is more complex than a frozen rock. It is a porous, fragile structure with volatile ices locked within, perhaps sculpted in the cold outer disk of another star billions of years ago. Confirmation came from a completely different angle, literally. In early October, as the comet passed near Mars, the European Space Agency's ExoMars Trace Gas Orbiter turned its camera, CASIS, toward the visitor. Despite not being designed for such distant targets, the orbiter captured a faint white blur surrounded by a misty halo, the coma of 3I Atlas, faint but unmistakable. From Mars's vantage, the comet was about 1,000,000 times dimmer than the planet below. Yet the image confirmed activity, a living, venting object. It was like watching two worlds exchange glances across space. Mars, a relic of our own system's past, and a comet from another, both bathed in the same sunlight. Each interstellar visitor has rewritten the rulebook. Oumuamua, the first, arrived in 2017, dry, tumbling, strangely metallic, accelerating in ways we still debate. Then came Borisov in 2019, a textbook comet, but rich in carbon monoxide, a clue that it formed in a region colder than any in our solar system. Now, 3I Atlas, the water bearer, 3 messengers, 3 different stories. Oumuamua whispered that not all interstellar bodies are icy. Borisov told us that some are frozen ghosts of distant Kuiper belts. And Atlas now tells us that even across light years, the recipe for water, the chemistry of life, appears again and again. Every system, it seems, brews its own version of the same cosmic potion. But there's a twist that's haunting astronomers right now. As we speak, 3I Atlas is vanishing behind the sunday. By October 21st, 2025, it reaches superior conjunction, slipping directly behind the solar disk as seen from Earth. Every telescope goes blind. The world's largest mirrors, the most sensitive spectrographs, all forced into silence. Even space observatories such as SOHO, Stereo, Parker Solar Probe, and Solar Orbiter can't help. The comet is too faint, too close to the glare. At magnitude 12, it's below the detection threshold of their coronagraphs. For weeks, there will be no new data, just equations and speculation. It's the astronomer's paradox. We can detect gravitational waves from black holes colliding billions of light years away, yet a single bright star, our own sun, can blind us to an event unfolding within our backyard. So we wait. When it reemerges in mid-November, 3i Atlas will appear again in the dawn sky. Fainter, but observable. The SWIFT team will resume ultraviolet monitoring, measuring how the hydroxyl emission evolves as the comet cools. If the OH flux drops gently, it supports the extended source model. If it collapses abruptly, the activity may have been a transient outburst, perhaps a crustal rupture or rotational fracture. Ground-based telescopes will chase the visible spectrum for signs of carbon radicals, C2, Cn, Comes, the fingerprints that map temperature and volatility. Infrared arrays will probe the thermal slope of the dust, constraining grain size. Polarimeters will watch for changes in scattering behavior, looking for shifts that betray surface transformation under solar heating. Every new data point is a clue to how alien worlds store and release their ices. The chemistry itself is already intriguing. Preliminary spectroscopy indicates that 3i Atlas may be carbon chain depleted, unusually poor in the C2 and Cn, bands that color most solar system comets green. Yet, paradoxically, images from August showed a distinct green hue developing around it. That contradiction suggests another process: prompt emission from ionized carbon monoxide, or even electrical excitation in the plasma environment. The sun's electric field and solar wind may be interacting with metallic dust in ways rarely seen before. There are even early hints of a nickel to iron ratio far outside solar norms, nickel lines blazing where iron should dominate. If true, that points to formation in a region contaminated by supernova remnants or the exposed core of a differentiated planetesimal exotic origins that would explain both the metallic dust and the high thermal resilience seen so far. A comet forged in the ashes of another star, now dissolving in our light. The implications go far beyond curiosity. Water is not just another molecule. It's the great enabler. Wherever water goes, chemistry follows. On Earth, it became the solvent of life, shaping mountains, oceans, and the cells within us. To find it venting from an interstellar comet means the chemistry of habitability is not confined to our solar system. It is written into the physics of planetary formation itself. If comets like 3i Atlas are common, if they drift between stars carrying water and organic precursors, then the galaxy may be constantly seeding itself with the ingredients for life. Each solar system may inherit not only dust and gas, but molecular memories from the systems that came before. We might be living in a universe where life's chemistry migrates system to system across cosmic time. But science, as always, demands patience. We need the second act of data, post-conjunction recovery, to confirm what is truly happening. If the water production continues after perihelion, it means 3i Atlas has a deep, porous interior feeding an extended coma. If it fades abruptly, it was a surface event, a single exhalation of trapped ice. Either way, it will redefine our understanding of interstellar material strength, volatile content, and thermal evolution. The next critical date is December 19th, 2025, when the comet reaches its closest approach to Earth at about 1.8 AU. By then, its brightness may decline. But our largest telescopes, Gemini, Keck, the VLT, will have the sensitivity to dissect its spectrum in detail. They will look for the isotopic ratios of hydrogen and oxygen in its water vapor. Those ratios are the cosmic fingerprint of where the water formed. If the deuterium to hydrogen ratio matches Earth's oceans, it would hint at universality, the same kind of chemical nursery that gave birth to us. If it diverges wildly, we'll know that other stars forge water under very different rules. Either outcome expands our perspective. There is also the matter of motion. Every active comet experiences non-gravitational acceleration, a subtle push from its own jets. In Oumuamua, that tiny thrust caused an unexplainable change in trajectory, igniting years of debate about its true nature. For 3I Atlas, we will be watching closely. High-precision astrometry after conjunction could reveal micro-accelerations that trace the orientation and power of its outgassing. If the extended source model is right, the net thrust should be small and isotropic. If it's asymmetric or time variable, we may discover jet structures or even fragmentation events hidden within the coma. Each possibility tells a story about the internal architecture of a body built under alien conditions. Behind every instrument and data point, there is also the human drama. Hundreds of researchers across the planet, professional astronomers, amateurs, mission engineers are connected by frantic threads of emails, late-night Zoom calls, and emergency observation slots. They know they are living through a transient miracle, an interstellar object within reach of our instruments. Once it leaves, it will never return. Its eccentricity greater than 1 guarantees it. Every photon captured is a postcard from another world, and there will be no second delivery. For me, as a physicist, what moves me most about this discovery is not just the chemistry, but the continuity it implies. We used to think of our solar system as an island, complete unto itself. Now, with 3 interstellar visitors in less than a decade, we see the opposite. The galaxy is porous. Material drifts between stars, carrying stories, elements, perhaps even prebiotic compounds. When I lecture about this, I often remind my students that physics is the story of universality, that the same equations governing an apple falling from a tree also describe a planet orbiting a star. Now we see that chemistry too is universal. Even across the gulf between suns, nature writes in the same molecular language: hydrogen, oxygen, carbon, nickel, iron. The building blocks do not care whose light they orbit. That realization should humble us. It means we are part of a galactic continuum, a network of worlds exchanging matter and information through time. And yet, the scientist in me cannot ignore the risk and suspense. 3I Atlas is currently plunging toward its perihelion, skimming the edge of the sun's most violent electromagnetic fields. What happens there could change everything. The solar wind, magnetic turbulence, and coronal mass ejections could strip the comet, fragment it, or ignite an electrical discharge across its ionized dust. The object might brighten dramatically or vanish altogether, breaking apart unseen behind the solar curtain. When it reappears, it could be reborn or gone. That uncertainty is what keeps the global astronomy network awake at night. In the coming months, as the data blackout lifts, all eyes will turn again to the dawn sky. Swift will resume ultraviolet scans. Mars orbiters may attempt follow-up imaging, and the great Earth-based telescopes will hunt for the spectral fingerprints of a world that is leaving us forever. Whatever they find, The message is already clear. Water, the molecule that shaped life on Earth, is not unique to us. It condenses in the cold of alien disks, rises between stars frozen in ancient ice, and evaporates again in the warmth of a foreign Sunday. For the first time, we have caught that process in the act. Perhaps someday, long after 3I Atlas has vanished into the darkness, another traveler will cross our path, carrying new clues, new chemistries, perhaps even organic molecules more complex than any yet found. And when it does, we'll be ready. Our instruments will be sharper, our telescopes faster, our curiosity undiminished. Because this is what science does best. It turns fleeting wonders into lasting knowledge. So tonight, when you look up and see the stars, remember one of them sent us a message, a whisper of water, a drop from another world, and somewhere in that vapor, drifting across the void, may lie the proof that life's chemistry is truly universal. When astronomers first detected 3I Atlas emerging from deep interstellar space, it seemed like a straightforward discovery. Humanity's third confirmed interstellar comet following Oumuamua 2017 and 2I Borisov 2019. An exciting addition, but not a paradigm shift. That assumption did not survive the data because what 3I Atlas is doing now is unlike anything in the known catalog of celestial mechanics. Harvard's leading astrophysicist has publicly stated that its behavior cannot yet be explained without invoking non-gravitational energy sources. He stopped short of saying technology, but the implication hangs in the air. 3I Atlas follows a hyperbolic orbit, meaning it is not bound to the Sunday. Its incoming velocity, 58 kilometers per second, and trajectory through the ecliptic prove it originated outside the solar system, likely from the cold outer region of another star. The chance of intercepting such an object is vanishingly small, roughly equivalent to finding one particular grain of sand across every beach on Earth. Early estimates suggested a modest nucleus, 5-6 kilometers wide, coated in volatile ices. Standard comet behavior was expected. Gradual warming, slow outgassing, a predictable coma. But by late August 2025, that model was already obsolete. The coma surrounding 3I Atlas began expanding at an exponential rate, faster than any natural model allows. Within 3 weeks, it exceeded 4,000,000 miles in diameter, over half the width of the Sunday. For comparison, the planet Jupiter, 88,000 miles, could fit comfortably inside. Instruments from Hubble, JWST, and the Very Large Telescope cross-checked each other. No calibration errors. No processing artifacts. The figures were real. This rate of gas and dust ejection requires energy outputs thousands of times greater than any comet previously observed in our system. Even accounting for CO2-driven jets, the math does not close. The expected consequence of such violent outgassing is structural failure. In 2020, Comet Atlas C divided by 2019, Y4 brightened dramatically before exploding into dust under its own internal pressure. By every simulation, 3I Atlas should have met the same fate. It did not. Despite ejecting mass at extreme rates, it remains intact, a sign of unprecedented material strength or internal cohesion. High-resolution imagery from Hubble revealed that the coma is not smooth or symmetrical. It shows multiple active jets emerging in stable orientations, not the random outbursts typical of natural comets. These jets appear to repeat in timed intervals, as though following an internal rhythm. The nucleus still unresolved, must be dense and structurally reinforced, capable of withstanding forces that routinely destroy ordinary comets. If its estimated ices are real, then its tensile strength exceeds any naturally accumulated aggregate by several orders of magnitude. At this stage, some researchers began to speculate about non-volatile materials embedded in the core, possibly metallic inclusions. Spectroscopy soon confirmed it. The James Webb Space Telescope detected a composition dominated by carbon dioxide, with water vapor unusually depleted. For context, typical solar system comets are water-rich and CO2 poor. This inversion implies 3I Atlas formed in an extremely cold protostellar zone, where carbon dioxide condensed before water ice could exist. Even more unusual were the trace metals. The VLT spectrographs detected strong nickel emissions, but no iron at equivalent wavelengths, an anomaly. Weeks later, as the comet moved inward to 2.6 AU, iron lines appeared suddenly, and the Nephi ratio collapsed by nearly an order of magnitude. The best current model suggests both elements exist as organometallic compounds, nickel tetracarbonyl and iron pentacarbonyl Fe, which vaporize at slightly different temperatures. This would explain the timing difference. Nickel sublimates first, iron later. It's the first time such compounds have been directly inferred from an interstellar body, providing evidence of complex chemistry in other planetary systems. For months, the comet appeared devoid of water, reinforcing its CO2-rich classification. Then, in July 2025, NASA's Swift Observatory detected hydroxyl gas OH in ultraviolet spectra, a clear byproduct of water photodissociation. Problem: the detection occurred when the comet was 3 AU from the Sun, far too cold for direct water sublimation. Calculations estimate 40 kilograms of water released per second, equivalent to a fire hose eruption in deep freeze. No model predicts this. The explanation now favored is that micron-sized dust grains coated with ice were expelled at high velocity, exposing water to solar radiation mid-flight. That would allow evaporation to occur far from the nucleus, a mechanism never before observed at this scale. Together, the metal anomalies, CO2 dominance, and remote distance water loss mark 3I Atlas as chemically unique among all known comets, interstellar or local. In September, long exposure imagery from Hubble and several ground observatories reported an additional feature, a faint forward-directed streak of coherent light, a narrow emission beam aligned with the comet's velocity vector. Initially dismissed as a processing artifact, the feature was later detected independently in Chile and Hawaii. If genuine, it violates one of astronomy's oldest rules. Cometary tails always point away from the Sun, driven by solar radiation and plasma wind. A forward-pointing, collimated emission has no natural analog. Some hypothesize a plasma jet effect or electrostatic focusing under magnetic interaction. Others quietly raise a more radical option, a controlled emission, perhaps for stabilization or communication. No conclusive mechanism has been identified. Now, the story reaches its most dramatic stage. In late October 2025, 3I Atlas will reach perihelion, its closest approach to the Sun, at 1.36 AU, just inside Mars's orbit. Here, solar radiation and tidal stress peak. Ordinarily, this is the decisive moment. The comet either survives or disintegrates. But there's a twist. During perihelion, 3I Atlas will pass directly behind the Sun relative to Earth, a configuration known as superior conjunction. For several weeks, it will be completely invisible to every optical and infrared telescope. Even space-based instruments like JWST will be blinded by solar interference. This means the critical hours when the comet experiences maximum heating and gravitational stress will be entirely unobserved. Some researchers consider this an unfortunate coincidence. Others note it would also be the ideal geometry for a gravity-assist maneuver, allowing an intelligent probe to decelerate or alter its trajectory unseen. When 3I Atlas reemerges from behind the Sun in November 2025, several outcomes are possible. Fragmentation. The coma disperses, confirming a natural but fragile origin. Case closed, an extraordinary comet, not technology. Survival intact. No breakup, despite maximum stress. Implies internal reinforcement or unusual composition. Probability of non-natural structure increases. Trajectory change. Any sustained deceleration or course deviation beyond outgassing models would suggest active control, a result that would redefine our concept of interstellar objects. The European Space Agency's JUICE and Mars orbiters will monitor the reappearance window. Initial tracking will focus on velocity, expected 67.9 kilometers per second, and spectral shifts in the CO2 and metal lines. If the numbers hold, the story quiets. If they don't, humanity's view of natural objects will never be the same. At minimum, 3I Atlas has already expanded our understanding of cometary physics. It demonstrated coma expansion rates beyond known limits, revealed organometallic chemistry operating in interstellar ices, provided the first live observation of water emission at extreme distance, showed structural strength inconsistent with fragile comet models. At maximum, it may represent the first artificial interstellar visitor ever detected. Either outcome is transformative. A natural explanation rewrites chemistry textbooks.